done this before. In grade 10, you already graphed lines. Do you remember graphing lines and shading either above or below? Remember the shading questions in grade 10? Some people are yes, some people are no. We're going to do the same thing with quadratics. So what happens to have a quadratic inequality is your equal sign is replaced with a greater than or less than sign. So I said I would review something from grade 10. In grade 10, you would have had questions like this. And in grade 10, you would have learned that, okay, could I graph y equals 2x minus 3? Right? How do you graph y equals mx plus b? You start with your y-intercept being minus 3. So I know that my y-intercept is at 0 minus 3. The 2 represents my slope with a rise over run. I can think of that as 2 over 1. So my slope means that I go up 2 over 1, find another point. Up 2 over 1, find another point. And this would make a straight line if I joined them. In an inequality question, sometimes we draw the straight line, and sometimes we draw the straight line but make it dotted. Do you remember if in this inequality, it should be a solid line or a dotted line? And the difference is whether the equal sign was included. Do you remember that? The equal sign is included, you draw a solid line. If the equal sign isn't there, the line isn't included. So this one doesn't have it, so we would draw our straight line, but have it dotted. And then finally, in an inequality, this is sometimes true and sometimes not. For example, sometimes you use a test point. Pick a random point anywhere. Let's say I choose this point right here, 0, 4. When I plug in 0 for x and 4 for y, question mark, is this true or is this false? If I plug in 0 for x, oh, I didn't plug in 0 for x. Plug in 0 for x and 4 for y. Do the math. I would get 4s, it would be on the left side, obviously, and on the right side I get minus 3. Is 4 greater than minus 3? True. Okay? With an equal sign, it would definitely be false. 4 does not equal minus 3. But with a greater than sign, it's true. So we know that this point is true. And in an inequality, if you find a point that's true, that will mean, and we used to shade this, I like using crayons, this whole section will be true. Any point you choose in this section will be true. Let's try another one. Let's say I chose -3, 0. If you plug in -3 for x, you're going to get -6 minus 3, -9 on this side, and y is 0. Is 0 bigger than -9? Yes. But any point you choose in this section will be false. Labeled it in red. 2 times 4 is 8. 8 minus 3 is 5. Is 0 bigger than 5? No. So one of the things that we're going to have to do in this unit is shade. And we have to shade the right section. One way that you can find out if a section works is try a test point. Okay? Sometimes people say, I like to try 2 test points, because if I make a mental math error on my first test point, I couldn't make everything work. So we tried both the blue point and the green point, and they both worked. They were both true. Then we tested one in the other section, and sure enough, it didn't work. So this would be the shaded region. Some people use the test points to figure out which section to shade. Some people use just the symbol. Y has to be, equal sign there, Y has to be bigger than the line. Here's my line. My Y values go up and down. If you took this point on the line, where are the Y values bigger than that point? Are the Y values bigger than that point when you go up? Or are the Y values bigger when you go down? Y values will always be bigger when you go up. So that's another way some students use to know which place to shade. Should I shade above the line? Yes, because I want my Y values to be bigger. If my Y value was less than, it would tell you need to shade below. And you can take any point on the line and say, if I'm shading above, this would be the part that would be shaded. So this is a review of shading from grade 10. Now, in grade 11, what's the difference? We start shading with parabolas. Okay? So off to the side here, I would like you to write the following information. Okay? And that was a review of grade 10. We're going to do some shading here in grade 11. We're also going to do some solving in grade 10, grade 11 as well. So the notes that we're going to put off to the side here. Some steps for how to solve a quadratic inequality. And solving a quadratic inequality is going to be very similar to solving a quadratic equation. So if you had a quadratic equation with the equal sign, just like we did before, you have your 3 techniques to solve it: completing the square, quadratic formula, and factoring. But in order to use any one of those, the first thing we like to do, right, if you're going to use your quadratic formula or you're going to factor, you need to make one side equal to 0. One side of your equation. Then we're going to solve this just like we did with quadratic equations, by factoring or the quadratic formula. And that will find out where it's equal to 0. And then we're going to use test points to find out which intervals are true, or use the graph to find out which parts are true. And finally, anytime you solve something, you have to write the solution. Once you find out where something is true, you're going to write the solution. So they've got a diagram here that sort of shows what's going to be happening. Sorry, let me know when you're done writing it down. Is everybody good? Almost. Shortened periods this afternoon because of parent teachers. But you guys are lucky, math is in the morning. Still get math all the time. Okay, so what do we got? They say, here's a quadratic function. Y equals x squared minus 2x minus 3. You could factor this, oops, and figure out that you have x-intercepts at -1 and +3. So we have 3, 0, -1, 0. Those are our x-intercepts. This is the graph of y equals x squared minus 2x minus 3. And now we're going to be solving the following equation. X squared minus 2x minus 3 has to be bigger than 0. Okay? So there's two ways that we can go about this. First of all, you're going to find out by factoring, probably in this one you would use factoring, you're going to find out that it's equal to 0 at those x-intercepts, right? I could factor this, make it equal to 0. If it was equal to 0, I would have x minus 3, x plus 1, so x equals +3, and x equals -1. But now, we're not solving for where it's equal to 0. We're trying to solve for where it's bigger than 0. Okay? Could you tell me an x value that makes that true? Do a little bit of mental math. There's tons of x values that make it true. Can you tell me one x value that makes it true? And then, can you find another x value that makes it true? Could you find the smallest x value possible that makes it true? Could you find an x value that doesn't make it true? Okay, I'm going to give you, that's lots to work on. Find something that makes it true. Find something that doesn't make it true. Do some test points, plug in some values for x. Like you can try, you're going to guarantee you're going to get one that works if you try like plug in 0. That's a really easy mental math one to do. You will either find one that works or one that doesn't work if you plug in 0, and you'll be half done. Okay. We're going to put here true, false. By the way, if I put in 0 for x, okay, is it true or is it false? Right, it'd be is minus 3 bigger than 0? No. So 0 would be in the false section. Did someone find one that works? What'd you find? 10. Mental math, that would be 100 minus 20 minus 3. Yes. That'll be 77. Works. So we've got one that works, one that doesn't work. Can you find another one? Did someone find a different one that works? Anything over 3? I'm not sure if anything over 3 will work. But I want a specific, like, give me a specific number. 4. Does 4 work? 16 minus 8 is 8, minus 3 is 5. Is 5 bigger than 0? Yes. And then the question becomes, what's the smallest we could find? Right? What happens if I try smaller than 4? If I try 3? Well, if we try 3, can you see that 3 was one of your x-intercepts? 3 makes it equal to 0. But is 3, is 0, if you plug in 3, is 0 bigger than 0? No, it's equal to 0. So 3 would fall into the false ones. So is 4 the smallest number that works? Smallest whole number. What happens if I put in 3.5? Would 3.5 fall into the true part, or would it fall into the false part? And now that we're working in decimals, now the mental math is like, oh. Right? Can you see that? So we need a better system to figure this out. Because you don't want to work with decimals. Because I'm going to tell you that 3.5 is true. 3.1 is true. 3.00007 is true. Anything slightly above 3 will be true. 3 won't work. Anything slightly below 3 won't work. So, it says, use test points to find which intervals are true and which intervals are not. The key thing, sometimes with the test points, we will make a number line and we will label 3 on here and minus 1, which match up with our x-intercepts. And we know that 3 and 1 cannot be part of the solution because that's where it's equal to 0, and we need it to be bigger than 0. Okay? And we just tested a number. When you tested 10 and found out it was true, that will mean that this entire section above 3 will be true. You can try 7. It works. Try a billion. I hope you can see that a billion is really going to work. Because a billion squared is going to be huge. Minus 2 billion, minus 3, definitely will be bigger than 0. But anything in this section, because we tested 0 and it didn't work, anything between -1 and 3 is not going to work. What about something less than -1? We didn't test that. We could pick a number less than -1. Anything less than -1? -2. Okay. -2. If you plug in -2, what's this going to be? 4. This is going to be plus 4 minus 3. It's going to be 5. It's true. So this whole section will be true as well. So this is step 3. If you use test points to find which intervals are true, we make a number line and split it up with intervals of where it's equal to 0. We add our solutions on there where it's equal to 0 and then can check whether it's true or false. It also says, or use the graph. Here's the graph. Can you see on the graph that when I am in this section here, bigger than 3, are my y values bigger than 0? Because this is, these on the graph is what's equal to y. So we can replace that with y and ask, are the y values bigger than 0? Absolutely. The whole graph is bigger than 0 there. The whole graph is bigger than 0 here. These sections would be true based on the graph. But this section in the middle, all the y values are less than 0. So we can also see the solution from the graph. And this is how we can solve a quadratic inequality. So some more things to highlight on here. Okay, we call the x-intercepts of a graph the critical values of a quadratic function. What we do is we draw a number line, and then on the number line represent the critical values either with open circles like we did here, or closed circles. And you're going to, if you want to put a little note, anytime you have greater than or less than, you'll use open circles. Anytime you have greater than or equals, or less than or equals, we're going to fill in those circles. And basically, the open circle means that that answer cannot be part of the solution. The closed circle means it can be. Now, the circles that we put on are where it's equal to 0. So if it's greater than or less than, it doesn't include when it's equal. That's why it's an open circle. When it has the equal sign, greater than or equal, or less than or equal, then we will include and fill in those circles. So if you want to highlight that as well, open circles are shown to be that they're not part of the solution. So what does this look like as an official question? Let's go to example 1. We want to solve this equation. First of all, you will make one side equal to 0. This one can be factored. And most of the questions that we do in the inequalities unit, they can be factored because the textbook wants nice answers for solutions. So we get more nice answers. So a lot of times these questions can be factored. This is a really, as far as checking if it can be factored, this is one of the easiest factoring ones there could possibly be. Because with 3x, what's your only option? Your first ones have to be 3x and x. Your last number is a 1. 1 is beautiful because what's your only option? 1 and 1. We've had no options so far. The only thing you have to think about is positive and negative signs. We want a positive 2x, so when we think about our outside or inside, the only way you're going to get a positive 2x is if the 3x is positive and the 1x is negative. And just like solving, when is it equal to 0? It's equal to 0 at 1/3. It's equal to 0 at -1. And so on our number line, we would have, well, -1 would be here, 1/3 would be here. Do we write open circles or closed circles for this question? We're going to have to either draw these circles and fill them in or leave them open. And this one is going to be open circles because there's no equal sign. Now, we have to figure out which sections are true, which sections are false. We can either use test points, or we can use the graph. Okay? Now, I'm going to tell you the graph is easier, but when you get to calculus, for some of you who are taking calculus next year, when you get to calculus, the test point idea comes back, and we use it again in calculus. So I'm going to start with the test point idea to show you how the test point idea works. Then I'm going to show you the graph as a way to check. Even though the graph method is easier now, you need to know the test point method for calculus later. So the test point method would be, do you know a number bigger than 1/3? I hope so. And you can choose any number bigger than 1/3. And you're going to have to plug it in. So some of the choices you're going to make are going to be mental math related. I probably wouldn't pick 7.27 because that mental math is going to be painful. But what would be easy ones that you could do in your head? 1. 1 is bigger than 1/3, sure. This would be 3 times 1 plus 2 is 5. 5 minus 1 is 4. Is 4 less than 0? No. This section then, everything in that section will be false. So we can do one test point, and then we know everything in that section will be false. In between -1 and 1/3, 0 is a beautiful one to use. Anytime you can use 0, mental math is easy. 0 plus 0 minus 1 is -1 less than 0. Yes, we know this section is true. A number less than -1, -2. -2 squared is 4. 4 times 3 would be 12. This will be -4. 12 minus 4 is 8. Minus another 1 is 7. Is 7 less than 0? No. It is false. You can use your test points in your original equation. That's what we did. You can also use your test points in the factored form. And I want to show you something with test points in the factored form that can be, it's mental math, but not exact mental math. So you know how we found out this first section was false? Okay? I'm going to pick a number in this first section. I'm going to pick something quite a bit bigger than 1/3. I'm going to pick 10. And I'm going to look at the factored form, but instead of actually figuring out the number, because it's pretty easy, 10 plus 1 is 11. But instead of actually figuring it out, can you see that when I plug in 10, this factor is positive? Plug in 10 here, this factor is positive. And if I have a positive number times a positive number, I'm going to get a positive number. Is a positive number less than 0? No, that section would be false. Watch what happens when I plug in 0. This part would be positive when I plug in 0. This part would be negative when I plug in 0. A negative times a positive will be a negative number. Is a negative number less than 0? Yes. That would tell me that section is true. So we can also use the factored form and use mental math just thinking with positive and negative numbers as a shortcut. Now, how would we use the graph to make this even faster? Can you see that this is a parabola? What did we solve for on the parabola when we did the solutions? The solutions are the roots, they are the zeros, and what's another word? The x-intercepts. So we know that on our graph, at -1 we have an x-intercept, and at +1/3 we have an x-intercept. What else do we know about this parabola? Does it open up or does it open down? A is positive, It has to open up. I don't need to label exactly where my vertex is. I just have to have a picture of the parabola. What are we looking for? We are looking for when is the parabola less than 0. In other words, when are the y values, because the parabola would be y equals this, when are the y values less than 0? Can you see that this section is true? But in these sections, it's false. So that is why I say the graph is quicker than the test points. But I want you to do the test points because that's going to help you in calculus later. Use the graph as the way to check your test points, if you were right or if you were wrong. So the last thing we need to do is to write our solution. We know the solution is true between -1 and 1/3. We have two ways that we're allowed to write our solution. There is something called set notation. In set notation, you would write your solution as our x values have to be between -1 and 1/3. And there's also an interval notation for a solution. Interval notation says, what's your smallest value? -1. What's your biggest value? 1/3. And we include everything in between there. But we don't include -1, so we use a round bracket. And we don't include 1/3, so we use a round bracket. And you have used set notation and interval notation before when you do domain and range. So you might be remembering them from domain and range. We use them for solutions of inequalities as well. All right, we're going to do another example together, but first of all, I'd like you to circle 4, 5, and 6.